So we learned two things yesterday that will relate to this problem, and it's a little bit weird, and maybe I didn't do the best job of tying it all back together to the concept. So we just learned two concepts of mutually exclusive, I'll put ME, and then independent. And we learned different formulations for these, but one thing that we learned right here is that if two things are independent, that the probability of A and B has to equal the probability of A times the probability of B. That's one thing that we learned about independence. And maybe you didn't really remember that formula, that concept that we talked about, but there we go. Let me just fix something real quick. All right, just to make this very clear. Now, the other thing we learned is that if two events are mutually exclusive, the probability of A and B happening has to be 0. Because these are two events that can't both occur. That's what mutually exclusive means. So if A happens, B can't happen. If B happens, A can't. They are mutually exclusive. It's impossible for these two to happen together. So let's kind of look and see what we've got. We already know that the probability of A and B is 0, so we know for sure right now they are mutually exclusive. So I can't, well, the only one I can rule out is this one. We know they are mutually exclusive, so that one doesn't work. The question is, are they independent? So the probability of A and B is 0. I'm going to put that in right here. The probability of A is 0.4, and the probability of B is 0.48. Now, I mean, we could do the math real quick. Why not? And that gets me 0.192. And we can see that's not true. So it turns out these are not independent. So they are mutually exclusive, but not independent. So there's your answer. And well, we could have crossed out this one earlier. They aren't mutually exclusive. So we actually knew that they were. So we could have crossed that one out too. But it doesn't matter. At this point, we found our answer. All right. Questions on that? We are actually going to be skipping the empirical probability activity because we're doing this on a Wednesday. We don't have as much time, and I think you'll benefit just the same without that. So we will look at some empirical probability to start off with. So when we talk about empirical probability, here's a histogram of temperatures. These are actual data points that were recorded, and we've got a lot of different data points here, but this is not to say it's been mathematically derived. It's just a series of observations. So what's the probability of a randomly selected day from this data being less than 70 degrees? All right, we could just walk through this pretty quickly. We are going to have another problem here. So less than 70 degrees, here's this. This is kind of like our normal CDF calculation, right? Where we're basically trying to figure out the area under the curve. With a normal distribution, we know the area under the curve is 1. We're going to have a different area. But I've got these three categories that are less than 70 degrees. And then I've got the total number of observations. If we count that up real quick, 52, 85, 89, 19. Is this 153? You guys can double my count.
And you got that just by adding up all those digits?
Yes. To clarify. Thanks for saying that. I just took all observations, added them up. All right, so if 153 is good, we know that we have 153 observations. And if I made a mistake on my adding up, you can still understand the concept. So if there are 153 observations of temperature here, and we add these three up right here, and that should be 33, the probability of a randomly selected day from this data being less than 70 degrees is going to be 3 out of 153. express this different ways. I mean, that is the probability right there. You could also frequently express it as a decimal, so 0.216. Yes, I am going to do things a little quickly today because I want to make sure that we have time to get through everything without pushing us right up to the bell. So assuming you guys were able to follow along with that, we know we have 153 observations. Go ahead and try this next one. See if you can do this. Okay, so empirical probability, you guys did a good job. We got the, like I said, the percent and the decimal represented. Empirical probability here just means that we're looking at actual data based on the observations that we have. We're not deriving this from some kind of a model. And we'll see some differences from that as we go through some of the practice problems today, where it'll tell us like basically there's an X% probability of something happening. And we can almost think of that as like, here's the model that we're given. Okay. So probability practice, this is just a general note to start out with that, and I won't do this for every problem, but for some of them, it is helpful to draw a picture. I showed some pictures yesterday using a Venn diagram, and you can show overlapping events A and B. So we'll do stuff like that today. I know I'll do it at least once. I don't know if I'll be good about doing it for every problem or very often. But if you find it helpful, see if you can find opportunities for that. So out of a box of 134 greeting cards, 57 of them were sympathy cards and 60 of them featured animals. If 20 of them weren't sympathy cards and didn't feature animals, are sympathy cards and cards featuring animals mutually exclusive? And just to start off with, you could probably see that probability problems are the kind that you're not just going to immediately say like, boom, I've got the answer, let's move on. I mean, if you're like me, you have to sit there and kind of read it twice and be like, wait, what? Wait, what? I think I get a little bit. And then eventually you read it and you're like, okay, now it's coming to me. So that's probably how you're going to be approaching a lot of these problems. So I just told you it's a good idea to draw a picture. So I'm going to do this. And we're going to work our way through it this way. This box represents all the greeting cards, 134 of them. Okay, now in there, and what I don't know is if they're mutually exclusive or not. So I've got one type of cards. If they're mutually exclusive, there's no overlap. These events can't both be true at the same time. If they're not mutually exclusive, there will be some kind of an overlap. Because in this region, this is where you're getting both of them happening simultaneously. So we have not determined yet if these are mutually exclusive or not. So now we want to kind of reason through this. Okay, so I know that I'm just going to start off with the assumption that they are mutually exclusive, just in the way that I draw it. And we'll find out if this is true. There are 57 of these that are sympathy cards. So I'll just put S for sympathy. It's 57. And remember, the box around it represents all of the 134 cards. In this, there's another subset of featuring animals. I'm assuming these are mutually exclusive, so I'm going to draw them that way. And there's 60 there. And then it also says there's 20 that aren't sympathy and aren't animals. So they don't fit in either category. They're going to sit out here. So if we think through this for a second, we can realize that this represents, as far as these categories go, this represents all possibilities. It's a sympathy card, it's an animal card, or it's neither one of those. And there's no other category that you could create. That should encapsulate all 134 cards. So now I can think of it this way. If these are mutually exclusive, then the probability of sympathy cards plus the probability of animal cards plus the probability of neither, I'll just put in for neither, should equal the probability of all those combined because they're mutually exclusive. A or, I want to say A or B, sorry. I should use the correct letters. So probability of sympathy or animal or neither. All right, so I mean, the upside of this is I just want to add this up. I know that I have a 134 out of 134 probability. Well, okay, I don't like the way I'm approaching this just yet, but there are 134 cards. And of those, I'll just say 57 right here represents, I'll do it this way. 57 out of 134 represents probability of sympathy. 60 out of 134 represents a probability of an animal. And 20 out of 134 represents the probability of neither. So now if I add that up, it'll make sense here at the end. If I add that up, I get 57 plus 60 plus 20 is 137 out of 134. And that, you can see, creates a problem. We have more cards in the box than there should be. And what do you think that means?
That they aren't mutually exclusive.
They're not mutually exclusive. And so what I should have done is drawn this where there's some kind of an overlap. And so that extra little bit, you can see we have 3 extra cards right here. There's actually going to be 3 cards in here. I can barely squeeze that in. 3 cards that are both sympathy cards and animal cards. All right, so just to answer the question very straightforward, are they mutually exclusive? No, they are not. You can have a sympathy card that also has animals. Okay, did that example make sense? Or any questions, I guess I should say. Okay, feeling good about it. So for the rest of this, we're going to take problems from the textbook and just run through it. Now, I do want to do this quickly, but as we go through it, make note of the question number. So if I'm going through it and you really aren't getting it, I'm going to ask you guys to contribute. But if you're not getting it, then just stick around afterwards and you can say, let's go back to problem number ... and let's go through that one slower. Okay, so in this one, we want to create the sample space, not create it. We want to list the sample space. So if we start off with A, remember we have these curly brackets for our sample space. We're going to roll 2 dice, just standard 6-sided die, and record the sum of the numbers. What are the possible outcomes?
Well, like if we add it up, it would be 2 through 12, right?
Perfect, you got it. So the outcome specifically in this case is 2 through 12. I mean, I probably would be better to write out 2, 3, 4, 5, but we get the idea. 2 through 12. Equally likely outcomes.
Yes.
Okay. And this is one of these that if you don't intuitively have an answer for it, that's okay. We can spend a lot more time reasoning through it. We know that on the first die, I get 1, 2, 3, 4, 5, or 6. On the second one, I could get 1, 2, 3, 4, 5, or 6. In fact, you might have seen a table like this before. If I add these together, I can see what my totals are. 2, 3, 4, 5, 6, or 7. I'm just adding the row and the column numbers. And then I can do this here. So 3, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8, 9. You can see the pattern that's going, which is why I'm not really thinking about this too much. All right, now notice, I'll just stop there. Of the 24 numbers that we've written down, only one of them is a 2. 2 of them are 3s. 3 of them are 4s. And you can probably see what's going to happen here. We're going to get a bunch of 6s and then a bunch of 7s going down in a diagonal, and then 8s. Look, I'm filling in the rest of it. All right. So there we go. Okay, so it turns out that 7 has the highest probability of being rolled, and every other number only has, well, has a smaller probability. So it turns out they are not the same probability. Again, I'm not going to dwell on that one too much. Family has 3 children. Record each child's sex in order of birth. So this, okay, let's kind of think through this one. And again, I don't want to take too long. What's the possibility that the first child could be what? Just throw something out.
Oh, 1 out of 2.
1 out of 2. Well, we're actually just going to pick male or female.
Male.
Male. Second one is
Female.
and the third one is
Another female.
okay. There we go. There's one possibility. I bet you guys could throw out some other possibilities. What's another possibility here?
Hold up, I got
All
this one. Oh, my bad. No, go ahead. Go ahead.
All females.
All females. Then
All males.
all males. All right, we can do this a little bit methodically. I'll just kind of skip to the end. So I'm just gonna jump through here. Female, male. Let's see, you got female, male, male, female, male, female, and female, female, male. All right, so this grows according to powers of 2, because, right, you got 2 options, male or female. And so we got 2 options, and we have 3 kids, raised 2 to the power of 3. We have 8. So if you had a 4th kid, there are 16 possible outcomes in the sample space. Okay, that's just kind of, are each of these equally likely to happen? We'll say across the populace.
Yeah.
Okay. Seems likely. Yeah, I think in this case, they are equally likely to happen. Okay, I don't want to go through all of these. Maybe I will say this. We could record the sample space of tossing 4 coins, the sample space for the number of tails. I will tell you this is not going to be equally likely to happen. So if you do want to come back to these, if this is still something that's a little bit confusing, we can do the last 2. I kind of want to jump ahead so that we're not taking too long on any one problem. Of course, the answers to these are not in the back of the book. But your homework tonight, you'll have some more things like this, and you can check your work. Okay, very quick on this one. We've got, all right, commercial airplanes have an excellent safety record. Nevertheless, there are crashes occasionally with the loss of many lives. In the weeks following a crash, airlines often report a drop in the number of passengers, probably because people are afraid to risk flying. A travel agent suggests that since the law of averages makes it highly unlikely to have 2 plane crashes within a few weeks of each other, flying soon after a crash is the safest time. What do you guys think about that?
Is it the same probability?
Same probability each time. There we go. So this is sometimes it's called the gambler's fallacy. You might have heard that before. The gambler's fallacy says if you flipped a coin, and it could be any random thing that happens. If you flipped a coin and you got heads 10 times in a row, it's like, okay, it has to be a tails this time. Well, no, the probability never changes. So the probability in general, we could assume that the probability of your particular plane being the unfortunate one, that doesn't change. Airline industry, okay, in this case, it's the opposite. People are saying it's been a really long period of safe flights. Therefore, it's like, uh-oh, is a crash due? No, not for exactly the same reason. A crash will happen again, but it's not like it has to happen on any particular flight. And with that very cheerful problem, let's move on to the next one. Okay, so we're talking about something called a probability distribution. And this is going to come into play more, but this is in the chapter. And if you read the chapter, you're already familiar with it. But basically, when you were looking at a set of certain number of outcomes and it represents the entire sample space, the probabilities of each outcome in the sample space have to add up to 1. And you cannot have a negative probability. Your probability has to fall somewhere between 0 and 1. So if we look at these 4, we've got 4 outcomes in the sample space. And here's the probability for this. So if I add this up, all the probabilities look good right off the bat. 20% is totally fine. But if I add this up, I get 0.8. So that distribution of probabilities does not work. It doesn't add up to 1. So if I go to the next one, 50, 30, 20, well, this is 1.1. That also doesn't work. The next one, 80 plus 10 plus 0.05 plus 0.05. So there we go. We got 100% right there. All of them fall between 0 and 1. This one's good.
So I've got a question about D. So since it's a negative number, would those two cancel out for the 50% and the 30?
Are you saying like, well, we're looking across the row. So you're saying like these two cancel out
And
we
then
get
you'd
one?
have like 100%? Because it, like, I don't know.
No,
Because can
you're
you
right.
have like a negative percent like that, or is it always like a positive percent?
It always has to be between 0 and 1.
Okay.
So, and then inclusive. So because of
Gotcha.
that, we violate it with this one right here. So this one doesn't work either. And of course, the last one we've got, it falls between 0 and 1 inclusive, and it adds up to 1. So it's a ridiculous one, but this is a valid probability distribution. I would say now your sample space is just 10% off. None of the others are part of the sample space, but there you go. Okay, it's just important to realize those couple properties about probabilities and the probability distribution in a sample space. Okay, so funding for many schools come from taxes based on assessed values of local properties. People's homes are assessed higher if they have extra features such as garages and swimming pools. Assessment records in a certain school district indicate that 37% of the homes have garages and 3% have swimming pools. The addition rule might suggest then that 40% of residences have a garage or a pool. What is wrong with that reasoning?
Aren't they not mutually or exclusive? So you could have a swimming pool and a garage.
That's exactly right. The addition rule that we learned only applies when that's mutually exclusive. So that says that the probability of A or B equals the probability of A plus the probability of B. But just like you said, you can have a garage and a swimming pool. In fact, it'd be very weird to have a swimming pool without a garage. No, it wouldn't be very weird in certain parts of the country. But there we go. So this has been violated. They are not mutually exclusive. We cannot do that. Very good. Did I skip one? No. Okay, although it's hard to be definitive in classifying people as right or left-handed, some studies suggest that about 14% of people are left-handed. So let's go with that. Since 0.14 times 0.14 is 0.0196, the multiplication rule might suggest there's about a 2% chance that a brother and sister are both lefties. What's wrong with this reasoning? maybe a way to phrase this is, what criterion has to be met to use the multiplication rule?
They have to be independent.
They have to be independent. So is it fair to assume that brothers and sisters are independent? Or is it possible that the probability of, the firstborn being left-handed increases the probability of the secondborn being left-handed? Do you think there's a link?
Is it like a genetic thing, being left-handed?
Maybe it's fair to assume so for this problem.
Well, let's assume so then.
Very good. And actually, I don't spend my time researching handedness, so I don't know if there's a genetic link. Maybe someone out there knows. Anyone have like a family that's got a higher than expected amount of left-handers in it? One of my brothers is left-handed, but I don't know anyone else in my family who is. Okay. So if there's no genetic link, then it would probably be fine to assume this. But let's go with there is a genetic link. There we go. We got some left-handers in the world. Okay. So now exercise 17, we don't need to worry about. We can still answer this question. So Harvard accepts about 9% of its applicants, Stanford 10%, Penn 16%. Jorge has applied to all three. He figures that his chances of getting into at least one of them must be about 35%. How did he arrive at his conclusion?
He added all the percentages together.
Okay, what assumption is he making in order to do that?
That he's smart enough to get into even one of these schools.
That is an assumption. And based on his reasoning, I'm doubtful. But what statistical assumption did he make?
They are mutually exclusive.
Mutually exclusive. So the idea is it possible to be accepted to Stanford and Penn and Harvard?
Yes.
It is possible. They are not mutually exclusive. This is some bad statistical reasoning. So, I mean, we don't need to answer that last part. Hopefully we all disagree with his conclusion. All right. So let's look at the next one. This is where it gets a little more mathy. So up until now, it's been more just conceptual. In a large introductory statistics lecture hall, the professor reports that 55% of the students enrolled have never taken a calculus course. 32% have taken only one semester of calculus. The rest have taken 2 or more semesters of calculus. The professor randomly assigns students to groups of 3 to work on a project for the course. What is the probability that the first group mate you meet has studied 2 or more semesters? So before we answer that, I'm going to create the probability of 0, the probability of 1, and the probability of, I'll just put 2 to rep 2 or more. And we already know what this is. Probability of 0 is given at 0.55. Probability of 1 is 0.32. So what does that mean the probability of 2 or more is?
0.13.
0.13. Now we are assuming here that these are mutually exclusive, but it doesn't take much thinking to realize they are. You can't have taken 0 and 1, or 1 and 2 or more. You fit into one category only. Okay, so now let's answer the question. What is the probability that the first group mate you meet has studied 2 or more semesters of calculus?
0.13.
Yeah, we're starting off easy. 0.13. What's the probability that they've taken some calculus?
0.45.
0.45. And if you can't see how that was arrived at, very good. We can see that some means at least one semester. And there you go. Add those two together, you got it. No more than one semester of calculus. What's the probability of that?
0.87.
0.87. Now, again, it's the same idea that if I add these two up, no more than one semester could mean 0 or 1. But another way of thinking about this is the probability of not 2. So the complement of 2. So it's going to be important to remember this complement rule because it is going to be very important to us later. So we can't always depend on just adding up all the other categories. So there we go. And at this point, it would be 1 minus the probability of 2, which would be 1 minus 0.13, and that's where we get our 0.87. All right, enough on that. Let's jump to the next problem. You're assigned to be part of a group in this. And okay, what's the probability that of your other two group mates, neither has studied calculus? And first of all, just tell me, what would you do to find that answer?
Would you do a 0.55 times 0.55?
There you go. We're saying it's the probability of no calculus and no calculus. And you'll see that I use this notation a lot. It's really important to understand it. And yeah, that will be 0.55 times 0.55. If some of you are getting a little not sure if we're making a mistake here, we're going to come to this later because maybe you're like, are we sure that's what we should be doing in this problem? Maybe there's something nagging at you that something's not right about this, but let's just go with it for now. So when you do that, we can get our probability. And what is that?
Uh, 0.3025.
3025. Okay, next we'll do the probability that both have studied at least one semester of calculus. So let's first of all, I'm going to bring this down here. Let's first of all write out what this probability would be in notation. It's the probability of what and what?
Oh, sorry.
No, go ahead.
Yeah, 1 and 2 and 1 and 2.
1 and 2. So we can write this two different ways. I'm going to show you two different ways of writing it. The probability of 1 or 2 and 1 or 2. Is there a different way we could write this? So we could say it's the probability of not 0 and not 0. Okay. So if you're with me on that, and both of these are correct, you can see one of them is a little bit simpler to write. So not 0, we already figured that out as 0.45. So I'm not going to get too caught up on the math of this. The hard part is reasoning what we're multiplying together. Okay, you guys can figure that out. So we can find our probability. The last one I probably need to run us through because this one seems like it's basically more the same, but there's a subtle distinction between this. All right, So the first one says, what's the probability that neither has done something? What's the probability that both have done something? The last one says the probability that at least one, and that's what you need to be on the lookout for, this phrase, at least one, because that's going to complicate your probability a little bit. So let's kind of run through what that means. Rather than trying to figure out the probability of this happening, when I see this at least one, I want to flip my thinking. And I want to think, what is the probability that I fail at getting this? So there's lots of outcomes where I have at least one of my group mates has a semester of calculus, but there's only one outcome where I fail at this condition. And that's whenever I have the probability of someone with no calculus and the probability of no calculus. So remember, this right here is the failure condition. Are you guys with me so far? So if I'm in a group where neither one of them has taken calculus at all, then I fail that condition. But now we can do this. Here's where I fail. So how do I find out the probability of success? I just take the complement of this. Notice it's not the complement inside the parentheses like I did here. Now it's the complement of this entire probability right here. So this, I will rearrange how I write this. So this is equal to 1 minus the probability of not having calculus and not having calculus. We're going to see some more examples of this today. So if this is not clicking right now, hopefully after 2 or 3 times it will come together. So now I just need to figure out what's the probability of no calculus and no calculus. I already have that. So 1 minus 0.3025 gives me my final answer. That's going to be 0.68, or no, I'm sorry. No, 0.6975. So that's a bit of a conceptual leap. And I'm going to pause there to see if you guys have any questions. So just in general, I will say this. If you see at least one as part of your probability, you're going to need to use some complement rule, and you're going to be taking the complement of failure. And I'll say, we'll get, like I said, we'll get to that again. So I'll repeat that and we'll run through the process again. But if everyone's happy with it for right now, I'm going to move forward. Okay, so this is where I was saying, some of you might have had this nagging feeling that something wasn't right. What assumption were we doing? When we said the probability of 0 and 0 was just 0.55 times 0.55, what allowed us to do that calculation? What statistical assumption did we make?
That like the total number of people you're picking from is the same and it doesn't subtract one of the guys that already got picked.
There you go. And we're talking about dependent versus independent, or sampling with replacement versus sampling without replacement. And that's going to be a big deal for us later. And we're going to learn more about that. So the assumption we made, piggybacking on what you're saying, is that these are independent. But I mean, there are some college classes where there's only like 20 people in the class, right? So if you take one out of the pool, then it's not the same probability anymore. It's not going to be 0.55 the second time around. It could be something else. So we assumed that it was independent, and in this case, it might not be reasonable to assume that. The probability doesn't stay 0.55 if you take someone out of the pool. Okay. But, for our purposes, it was still good for illustration for some statistics. Okay, according to Pew Research, the contact rate, that's the probability of contacting a selected household, was 69% in 1997, 76% in 2003. However, the cooperation rate, which is actually agreeing to interview, once contacted, is 0.58 or 58% in 1997, 38% in 2003. What's the probability of obtaining an interview with the next household on the sample list? And to get an interview, you first need to make contact, and then you need to get agreement. So what would you do here? Let's write the notation first. The probability of what and what?
The probability of contact and willingness.
And there you go, cooperation. They both start with C, so that's why I'm writing it out. But we need contact and cooperation in 2003. So is it fair to assume that we could just use the multiplication rule? Let me go ahead and answer that. It is fair to assume that in this case, and we're actually doing a little bit of conditional probability, though we're not explicitly saying it, but yeah, it is fair to assume that these are independent, that 38% is going to be constant no matter what the probability of contact rate is. All right, so anyways, 0.76 times 0.38 here. What's our probability? All right. You guys still with me?
0.288.
There we go, 0.2888. So is it more likely to get an interview in 1997 or 2003? We can do the same calculation, but using, so there's 2003, here's 1997. And what'd you get for your probability of 1997 interviewing?
Point 4.
0.4. Okay, so it looks like it was easier in 1997. Not too difficult on that, but I just wanted to run through that scenario. Okay, I only wanted to bring this up real quick. I'm not actually going through most of this, except the last question. This is actually something that's really a good thing to go through. Can disjoint events ever be independent? Can you be both mutually exclusive and independent? And to do that, I might actually jump to the next slide. Yeah, so I have a little bit of room to work here. I'm not answering this question yet. But remember, to be mutually exclusive, the probability of A and B has to equal 0. And the probability of A, this is mutually exclusive right here. So if it's independent, probability of A and B has to equal the probability of A times the probability of B. So we can see if there is an actual probability of things happening and it's not a 0 probability, then A times B is going to be greater than 0. So to be independent, your probability of A and B has to be greater than 0. Does that make sense? And this is assuming it's a non-zero probability. But to be mutually exclusive, it has to be 0. So this is our basic idea, that you cannot be both mutually exclusive and independent. So you cannot be both. You have to pick one or the other. All right, so that's kind of the mathematical way of thinking about it. But another way of thinking about it is this. If you have coin flip, that's the simplest example here. You can land heads or tails. We know it's mutually exclusive as a result. If I am trying to find the probability of, I've got one event and I'm going to land on it, heads or tails. It's mutually exclusive. But if I land on heads, then the probability of getting tails at that point has gone down to 0. All right. So, I mean, it's kind of a weird way of thinking about it, but your probability changes to 0 for any of the other mutually exclusive categories once you have gotten an outcome of one of the categories. So it does change your probabilities. All right. So maybe the mathematical way was a better way of thinking about it. Maybe that example helped some. But let's kind of jump ahead. The main takeaway is you can't have both mutually exclusiveness and independence. Okay. So now we can run into some more interesting math problems. We'll try and wrap this up. We might actually get this in before class ends today. A slot machine has 3 wheels that spin independently. So we're already going to know that these are independent. It's good to see that term. Each has 10 equally likely symbols. And they are 4 bars, 3 lemons, 2 cherries, and a bell. If you play, what is the probability that you get 3 lemons? So let's just kind of do the basic stuff real quick. The probability of a bar is what?
0.4.
0.4. Yeah, we'll put it in decimal terms. So 0.4. This is going to be pretty simple. Hopefully, I'm just going to do this. 0.3, 0.2, 0.1. Hopefully, you guys are good with that. Okay, what's the probability that we get 3 lemons? Let's write this in notation first. The probability of what? What would we write here?
I have a quick question.
Yeah.
What's that probability that's 0.1?
That's bell. Sorry, I already used the B.
Oh, I just didn't read that it had 1 bell. I see.
Oh, okay. So in notation form, what is our probability for part A? Probability of what goes in the parentheses? What would the first? Oh, go ahead.
Would it be getting the 4 or 3 lemons? So 0.3 times 0.3 times 0.3.
You are right. That's going to be our calculation. What I would start with is this: lemon and lemon and lemon. It is important to be able to kind of think through it in terms of the notation. I keep saying that, so hopefully you guys believe me. All right, lemon and lemon and lemon means it is going to be just what you said, Leo. It's going to be 0.3, and I'm just going to say 0.3 cubed. All right, we can do that. What's that going to be? 0.0729 or something. Did I get it right? No, it's 0.0729. No, it's 0.00729. Is that right?
0.027.
Okay. So there I go, trying to be smart. I don't know how to do things. I was thinking of 9. All right, so let me correct my errors. 0.027. Note to self, don't try and be smart. Okay, now we're good with that. You get no fruit symbols. So what are our fruits?
Cherries and lemons.
Berries and lemons. So again, we could write this different ways. I could say, this is going to be a pain to write out. You get no fruit symbols. So I'm going to say lemons or cherries complement. We don't want to get lemons or cherries, but I have to put lemons or cherries. And lemons or cherries complement. And lemons or cherries complement. Isn't probability fun? Okay. Now, I mean, the math of this works out pretty well. What is the probability of getting not lemons or cherries?
Is it 0.5?
0.5. So 0.5, we'll just do that cubed. Uh-oh, here I go. Trying to be smart. I think this is 0.125 this time. Okay. All right, I'm gonna skip the next one. That one's pretty easy. No bells, that one's also pretty easy. I'm not gonna go through and do the math of it, but basically it's the probability of not getting a bell and not getting a bell and not getting a bell. So if you want to go through that, if you want to put a star by this and come back to it, we can look at it. But I think the one that's going to be the tricky one here is the last one, because look, you get 3 lemons. That means all lemons, 0 fruit, all bells, no bells. So what's the probability of getting at least 1 bar? And that's what that phrase you need to be on the lookout for, at least 1 bar. And the trick to this one, like I said before, is we want to figure out what is the only way we fail at this condition. Because I could get 1, 2, or 3 bars, that doesn't matter. But the only way we fail at this is to get 0 bars. So I want to find the probability of no bars, so complement of bar, and no bars, oops, and no bar. Okay. So if I have that, no bar, no bar, no bar, and I figure that out, what this is going to tell me is the probability that I fail at this condition of getting at least 1. So at the end, I want to take the complement of all of this. Okay, I'm kind of pausing in between, so if there is a question, you can jump in at any point. So now I'm going to, before I plug in numbers, I want to do this. I'm going to say the complement of anything is just, so the probability of a complement, I've been doing this and we saw it yesterday, but I want to make sure it's very clear. It's just 1 minus the probability of A. So anytime I see the complement here, I'm just going to do this. 1 minus the probability of no bar and no bar and no bar. So the probability of not getting a bar, well, it's these 3 added together. So now is where I'm kind of jumping and doing quite a bit of math, or doing things a little quickly. So it's going to be 1 minus, looks like 0.6 cubed. And jump in if you need any help with that. So let's do that real quick.
It's 0.06, right?
Well, it's 0.6 because we're dealing with 30% chance of we can just add these three together. If it's a 40% chance of getting a bar, then 60% chance of not getting one.
Oh, yeah, I was doing it different.
No worries. 0.6 cubed, and then subtract that from 1. I get 0.784. So think about this when you're old enough to go gamble in Las Vegas. Now, it's generally more than 10 symbols on a wheel, I think. I actually don't gamble. I don't go to casinos. Again, it's because I teach statistics. But anyways, there's an 80% chance basically that you're going to automatically lose. So I don't like those odds, but maybe you do. All right. I'm going to call that good with that problem. In fact, we're going to have to call it good with the day, probably. This is another problem that kind of does the same thing, but it's looking like a real world scenario where it's a commuter getting stopped 15% of the time. So I encourage you to try these types of problems. If you do want to stick around after class, you can. I think, all right, maybe we could just finish it off talking about this one conceptually. Manufacturer places winning symbols on the caps of 10% of all Pepsi bottles. You buy a 6-pack. What is the probability that you win something? And the way to think through this one, and we don't have much time because I think you're out of here in 4 minutes technically. So the only way that we fail at winning is if we don't win on all 6 of these. So I want to say the probability of not winning, I could put it as the complement of winning. Maybe I'll just put of losing and losing and losing and losing and losing and losing. That's 6, right? I've got 6 bottles and I could lose on all of them. The probability that we win something is going to be the complement of that entire thing. So we only care about winning at least one time. If we win all 6, hey, even better. Okay, I will let you guys kind of explore that on your own. Your homework is right there. If you do want to stick around, please feel free to do so. Otherwise, have yourself a wonderful day, and I will see you guys tomorrow.